This is the Earth Science Classroom. Welcome back to the channel. This video is on a review of the Atmospheric Science unit. This is video 1. This will be on the atmospheric composition, atmospheric layers, each layer's description and definition, and looking at the temperature profile and looking at the pauses. So we have this graph and we have altitude on the y-axis, temperature on the x-axis, and we're looking at a starting point of around 15 degrees Celsius. About here. Now, the temperature profile is the side view of how the temperature changes with altitude as it goes through the atmosphere. So the atmosphere really goes from 0 up to around an average of 100 kilometers. Now, the difference between space and an atmosphere, this line is a not consistent, but a generic point of there being no more air molecules and it becoming what's called a vacuum. So it's the absence of air molecules defines space. Now space is full of other stuff, but there's no air molecules. So radiation can go through this vacuum and interact with our atmosphere from the sun. So the temperature is how many collisions there are between the air molecules to release the energy inside of it, and that's how we record temperature. So it's based on collisions. So this graph looks at the temperature going through the atmosphere from the surface, which is 0 up to around 100 kilometers or about 70 miles. So we first get colder, then we get warmer, then we get a lot colder, and then it starts to get warmer again. So if we just draw these horizontal dashed lines to where the temperature changes, the temperature pattern changes. So we have this decrease from the surface down to around minus 60. Then we have an increase in this part of the atmosphere going up to about minus 2 degrees. And then we have a decrease again going down to about minus 85. And then an increase again in this part of the atmosphere that's really high up. So we can say this is about 15 kilometers, this is 50 kilometers, and this up here is 85 kilometers. These lines that are called pauses, they pause because it's a change in what the temperature is doing. And this can separate the atmosphere into its 4 distinct layers. This would be the troposphere, as in the lowest layer, the layer by the surface, and this would be the tropopause, and this would be the stratosphere, the next one up, between 15 and 50 kilometers, and this would be the stratopause. So it's where the stratosphere starts to end and the new layer begins. This new layer in the middle is called the meso or mesosphere. Meso means middle, and this would be the meso or mesopause, again the end point or the ceiling or the roof of mesosphere, and the new layer starts, which would be the thermosphere, and thermo means heat. And this thermosphere can exceed up to around 3,000 kilometers away from the surface, and we start to gradually go into space, which again is the absence of air molecules, so can't really feel temperature. So the troposphere has certain conditions and certain attributes that we need to know. The troposphere gets colder, temperature gets colder as you go higher up into the pause, which is minus 60, and then obviously minus 60 it stops rising because it's too cold. Cold air doesn't rise, cold air sinks. That's going to start to create our GCMs, or our general circulation models around the atmosphere. Looking at the weather and climate exist in this layer mostly. There is some stuff in the stratosphere, but majority is in the troposphere. Weather is daily conditions and climate is long-term over a 30-year average. Our winds, our trade winds, our easterlies and westerlies all occur in the troposphere. Our jet streams and Rossby waves, they generally occur in the troposphere. And we have the majority of the atmospheric pressure and atmospheric mass in the troposphere caused by gravity, and also our human society and everything we do as humans basically is in the troposphere, except for any satellites or the space station, which is in the thermosphere. And the pause can range between 7 kilometers over the polar regions, North and South Pole, up to 20 kilometers over the equator due to the intense heat and rising air over the equator. So looking at the stratosphere, the next layer up, it's above the troposphere, and below mesosphere it's between 15 and 50 kilometers in altitude, so it has a thickness around 35 kilometers. It is obviously a larger layer than the troposphere. It has less mass and less atmospheric pressure. There's less air molecules up there, so the atmospheric pressure is less. The temperature increases with altitude, which is the opposite to the troposphere, and this is caused by the presence and concentration of ozone. Ozone is a gas that's made of 3 oxygens combined by covalent bonds. It's a very strong, larger molecule, and it's made up of the diatomic oxygen, which is O2, which we breathe, and the single oxygen, which is called atomic oxygen. So you add 2 oxygens plus 1 equals 3 oxygens, which is ozone. Now, this is formed because of ultraviolet or UV radiation that comes from the sun. It is a short wave radiation that's shorter than the purple wavelength, which we see as purple color in that rainbow, the 7 main colors, purple or violet, which is one side of the visible light spectrum. It's beyond that. So it's a shorter wavelength than violet. We call it ultraviolet. We can't see it. It's visible to our eyes, but it forms ozone by breaking down O2 into 2 single oxygens and then adds it onto the existing O2. So 1 oxygen plus O2 equals 3, and that's what we call ozone. And this molecule has a great property. It loves to absorb and eat ultraviolet light, as well as break it down. It absorbs it. That absorption of the energy is going to heat up the atmosphere around it, so therefore the stratosphere gets warmer with altitude because of the concentration of ozone at that altitude. It gets to the pores, which is around 50 kilometers, and then ozone starts to diminish. There's no more ozone at that altitude, so therefore it goes back into cooling down with altitude into the next layer, which is called the mesosphere. So now we have the meso or mesosphere. This means middle. Meso means middle. And it's above the stratosphere, it's below the thermosphere. So it's between 50 and 85 kilometers, about 35 kilometers thick. It really has no distinguishing characteristics except for it does decrease with temperature as you increase in altitude. So as you get higher in the mesosphere, it gets colder and colder and colder, down to a minus 85 degrees Celsius around that, which is the coldest part of the atmosphere. And that is where the mesopause exists, because then it starts to get warmer into the thermosphere. Now, the cool thing about mesosphere is there's enough air molecules due to the atmospheric pressure and also the gravity. There's enough air molecules that when a rock from outside of our earthly system, our planetary system, which we call an asteroid, when it enters the atmosphere, we call it a meteor. Now, this meteor is going to come through the thermosphere and enter the mesosphere. It's going to enter an area where there's a larger accumulation or concentration of air molecules, because you're getting close to the surface, and this added with the speed of entry of this rock being around 30,000 miles per hour, when it hits the air molecules, you get a lot of friction. And there's enough friction to cause the rock to actually combust and burst into flames. So you see this fiery rock coming through the atmosphere, and we call this a shooting star. Now, if it does go through the mesosphere, it is designed really to break down this rock to not have an impact on the surface, but occasionally these rocks do get through the mesosphere and the stratosphere and the troposphere and do make impact with the surface, which we then call that rock a meteorite. And they cause craters, and like with the dinosaurs and the KT extinction, they can cause a big issue for animals and life on the planet, mainly an extinction level event. So the mesosphere really is that first layer of defense where the air molecules could break down this space rock, this meteor, from eventually hitting the surface. Then we're on to the thermosphere. Now, thermosphere, thermo means heat or thermal energy, so we're looking at a layer that's heated. Now, where is it heated from? It's heated from the first kind of interaction with radiation from the sun, the EM spectrum. So it's going to be heated by radiation, by UV, by X-ray, by microwave. It's going to be heated by these energy wavelengths, and the individual air molecule is going to be heated. Now, because there's so little air pressure, there's 0.0001% of the pressure at the surface, the air molecules are really free to go really far away from each other. So if they get heated and have all this internal temperature and kinetic energy, the air molecules cannot collide with another air molecule because they're too far apart. Therefore, the actual air molecule can be really hot, up to 2000 degrees centigrade, but it cannot collide, and that's how we feel temperature. So the air molecule could be really hot, but the layer could be really cold. So there's a kind of an oxymoron right there. And then also this includes the ionosphere. The ionosphere is charged particles, charged ions and electrons that buzz around at this altitude, and they interact with the solar winds and the energy from the sun and create the aurora borealis, which is the northern lights, and the aurora australis in the southern hemisphere, the southern lights. Now you can see those in places like Iceland and northern Canada and the Arctic Circle and certain parts of Scandinavia. And also you could see the southern lights in Antarctica. It also includes the exosphere. Now the exosphere really is a separate layer. It's the fifth layer technically, and that can really extend up into space where space starts. But the thermosphere is the more common layer at the top of the atmosphere. Exosphere can be part of it. This part of the review is on the atmospheric composition, what's in the air, and the variable, trace, and aerosol components. So in discussing the atmospheric composition, we're discussing what the air is made of, what's in the air exactly. And this atmospheric layer is a gas layer, mostly. It has some liquid in it through the water cycle, but the gas layer is held in place by gravity, and it's freely moving because it's a gas, and this is a state of matter that it has certain behavior and certain characteristics, and it has a fluid property, a fluid dynamic. So it's constantly moving, air rising, air sinking. There's lateral movements at the surface, at the different pauses, but the gas is constantly moving whilst being held in place by gravity. And there's difference in pressure and temperatures, but it's a very dynamic part of our Earth. So the gases, we're looking at the top three, which make up the majority of, well, the top two that make up the majority of the atmosphere is nitrogen, which is N2, which is 78.08%, then oxygen, which we breathe, which is O2, which is 20.95%, and then the last one, which is a small kind of unknown gas, so it doesn't really do much, is called argon, and that is Ar, and that's 0.9%. So all that added up is around 99%. Now the other 1% of the atmospheric composition, the gases that make up that 1% that's left, could be a selection of helium, hydrogen, neon, argon, which we discussed, CO2, carbon dioxide, which is very apparent in the media and scientific literature about the effects of carbon dioxide and what creates it, also methane, which is CH4, and water vapor, which is H2O. Now, water vapor, CO2, and CH4, methane, they are what's called greenhouse gases, and they also called variable gases. Now, variable is a term that means it can change the amount. So water vapor can change from 1 to 4% based on environment and location, and CO2 and methane can also change over time. So when the dinosaurs were around, CO2 was 8,000 parts per million, and right now it's 420 on average. So it does change over time, and how long the Earth has been around can change a lot. And also the composition. So the first atmosphere Earth had was hydrogen and helium, and it slowly evolved and changed into what we have today, which is nitrogen and oxygen and argon. Then we have the aerosols. Aerosols are suspended particles, little bits of something. For example, pollen, which we have allergies from, grass and tree pollens, and dust, and particulates we look for in more industry and pollution. Different size of particulates between 10 to 2.5 micrometers. Look at sea spray, like the salty air you can smell by the coast, and also sand, like in sandstorms and dust storms, like in the 1940s in the Dust Bowl. And you also have a thing called CCN, which is called cloud condensation nuclei. These little aerosols or particles are used to help condense the water vapor and turn the water vapor with the CCN or the aerosols into rain droplets in terms of cloud formation. This part of the atmospheric review concentrates on adiabatics, why hot air rises, why cold air sinks, looking at atmospheric pressure, energy, and what's called kinetic energy in the air molecules. So part one of this would be to explain what an air parcel is. An air parcel is a unit or an area of the atmosphere that contains air molecules that scientists use to look at in more detail and more focus for anything that changes within this atmosphere. So we add heat, what happens? You can see it in a small, very isolated area called an air parcel, rather than taking the entire atmosphere as one big lab, which is extremely hard to do because it's so many different moving parts in the system. So you take a single air parcel to see what's going on. So if we're looking at hot air rising, you're going to have energy added to this air parcel. Now it could be added from the surface. Could be added from radiation, could be added from absorption of ozone in the stratosphere, but you're going to have energy, thermal energy added to this air parcel. So what's going to happen is you have these individual air molecules. I'm going to draw with these little circles. And it's within the air parcel. And the air parcel has a given volume. And there's a given density based on the amount of stuff in the volume, which is mass over volume. And there's also a given amount of atmospheric pressure that these air molecules exert on the air parcel. So we have these three factors to consider: volume, density, and pressure, all caused by the air molecules and how they move. So they move around because they're a gas and they're freely moving molecules. And the increase in thermal energy, you're going to increase the amount of movement, which means that they'll have more kinetic energy and also more potential and internal energy within the air molecules. Now, this kinetic energy will make the air molecules move more, and they'll be more excited, and they're going to move faster and in a greater distance. What's going to happen is that will apply more pressure onto the size of the air parcel, and it's going to make the volume change. Now what happens is the air parcel is going to increase in size, therefore increase in volume. And if you have the same amount of air molecules present inside the air parcel, then you're going to change the density. It will become less dense. It will become lighter. It will become more buoyant. It will become lighter and more buoyant. So this larger air parcel, because the air molecules are moving more and applying the pressure on the air parcel to get larger, it becomes lighter and more buoyant, and what's going to happen is it will rise up to a higher altitude. Hot air will rise. So this hotter air parcel that was at the surface, and the environment or the atmosphere around it is 20 degrees Celsius as shown, but the air parcel itself, because the addition of thermal energy becomes 25 degrees Celsius, that is warmer than the air around it. It's going to rise due to the reasons I stated earlier. The rise in air parcel will go higher in the troposphere, because it's the first layer, and at a certain altitude it gets to 10 degrees, but this rise in air parcel will start at 25 and then slowly but surely start to get colder, because there'll be a larger volume air parcel. Those really high, fast moving air molecules, because of the kinetic energy, they will start to not hit and collide as much with the other air molecules because of the larger volume with the same amount of air molecules, and that will cause the temperature to decrease. So the less collisions, the less temperature is released from the colliding air molecules, and therefore temperature of the air parcel decreases. Now, it will keep rising if it is warmer than the air around it. So if it's 15 degrees, it will still rise above what's stated here as 10 degrees. But if it cools down to 10 degrees, that air parcel will stop rising. It's the same temperature as the air around it, and it'll become what's called stable. So this is atmospheric stability. If it's going to rise up, it is unstable. It is hotter than the air around it. It's unstable and rise. If it is the same temperature, it will become stable and maybe even become colder than the air around it, and it would sink. So here's my air parcel. The larger volume of air parcel, after it's risen and increased in altitude, the same amount of air molecules start to not add too much pressure onto the air parcel. They start to move less and collide less. That will cause the density to start to change. It was low density, now it's starting to, with the air molecules becoming less energetic and occupying less space, the air parcel starts to shrink. And what you have is you get less collisions and less energy release, therefore it creates a lower temperature, and that also creates a decrease in the volume. So this air parcel that once was bigger and more buoyant and rose up because of the heat added, because the heat is not there anymore, it's been removed, the volume of the air parcel decreases and the density increases. It gets heavier, and this heavier air parcel is going to sink back down to a temperature that either will add more heat, or a temperature that is the same on the outside, and therefore the air parcel will become stable. So the stability of the air, or the air parcel, is based on the addition of thermal energy, and if that air is going to rise or sink or stay at the same altitude. So the term adiabatics is in relation to an air parcel's temperature and a change in temperature is caused by a change in pressure. So if you were to add more pressure, high pressure on the air parcel, it would actually decrease the volume, and increased pressure would cause the temperature to increase. If you lower the atmospheric pressure on that air parcel, it would get larger volume, and it would get colder. So you could have adiabatic cooling and also adiabatic heating. So this is to do with rising air parcel with adiabatic cooling, the lower pressure, the larger volume of air parcel, and obviously this happens with high altitudes when the air is rising. So on the flip side, in the opposite, is adiabatic heating. That is based on sinking air, an increase in pressure, which causes the volume of the air parcel to become smaller, and then there's more collisions due to the air molecules being closer. More collisions means higher temperatures. So based on the pressure would create a change in temperature. So adiabatics does not involve any adding or taking away of heat. It's just changing the size of the air parcel based on pressure. So atmospheric pressure is the combination of the mass of the air molecules plus gravity equals the weight of the air. Now obviously gravity is going a force of attraction down to the center of the Earth. So all of the atmosphere around the Earth, which obviously is a sphere, is being attracted down towards the center of the Earth, the inner core, the center of the mass of the Earth. So the surface pressure, or the surface atmospheric pressure caused by this weight of the air molecule plus gravity, is around 14.6 pounds per square inch. So when you wake up in the morning, the atmosphere exerts 14.6 pounds per square inch on your body. Now we're used to it, so we don't feel it. But we go up in the atmosphere and we decrease in pressure, then you're going to feel that change. If you're going to climb Mount Everest, you'll notice that there'll be a third less oxygen in your breath every time because of the change in pressure, and it makes the air molecules spread out. So when you breathe in, you're just breathing in less oxygen, and your body goes into fatigue, and there's health issues. Besides the weather and the elevation and the other issues, it's just the pressure changes. So the rule is the higher you go in the atmosphere, the less atmospheric pressure you have, because gravity and bringing all the air molecules down towards the surface, and below the first 50 kilometers, so the troposphere and stratosphere, you have 99% of the mass of the atmosphere in that layer. So that's where we are. So we have our oxygen, our nitrogen, argon concentrated around the surface of the Earth.